Okay, this is another perspective paper. Bunch of smart people get together and focus on a particular topic and come up with some sense of where we are and where we need to go in a particular theme, like here, theory and the future of land climate science. Land climate science is not something you hear all the time. You hear about land atmosphere interactions, land ocean continuum, and so on. But we know that land use change, etc., play a big role in climate variability and change. Climate over land, where humans live and the majority of food is produced, is changing rapidly, driving severe impacts through extreme heat, wildfires, droughts, and flooding. Our ability to monitor and model this changing climate is being transformed through new observational systems and increasingly complex Earth system models. But fundamental understanding of the processes governing land climate has not kept pace, weakening our ability to interpret and utilize data from these advanced tools. Here we argue that for land climate science to accelerate forwards, an alternative approach is needed. We advocate a parallel scientific effort, one emphasizing robust theories. That's why theory appears here first. That theories that aim to inspire, or their scientific effort aims to inspire current and future land climate scientists to better comprehend processes governing land climate and its variability and extremes and its sensitivity to global warming. Such an effort, we believe, is essential to understand the risks people face where they live in an era of climate change. So we talked a lot about, the Arctic ice loss, El Nino, or ocean warming, cyclones intensifying, but where we live, what's happening? Do we have a good handle on that? So they give some examples of where theory is stuck or needs to make progress and so on. I won't read all the details. It's a relatively short paper coming out of a meeting, I think, but you can still go back and read it. This is just a brief introduction as usual. Just my selection of what are the important points in the paper. Starting with their introduction, knowledge of some aspects of continental climate and the responses to global warming are well established. For example, we broadly understand why land warms more rapidly than oceans. We'll see a schematic soon. The intensification of extreme precipitation in a warmer atmosphere on land, and how surface runoff is influenced by loss of snowpack. However, knowledge of many other aspects of land climate is underdeveloped. The wet get wetter and dry get drier paradigm predicts an amplification of wet-dry contrasts as climate warms, but this paradigm does not generally apply to land regions. Neither does the poleward expansion of the Hadley cells. Lots of papers on each of these topics of Hadley cell and wet get wetter, some say rich get richer type of paradigm. Adding to this list is uncertainty over how evapotranspiration and soil moisture, both critical for humans and ecosystems, will be altered by a change in climate. Knowledge of numerous other facets of land climate is similarly unsettled, means not settled. Unsettled is slightly, anyway. From basic questions of what governs its mean state, variability, and extremes to how these facets may change with warming. Why are simulated land temperature changes more uncertain and more diverse across space and climate models compared with ocean regions? Why are the tropical rain belts broader and more mobile over land? And how will land humidity evolve as climate warms? Will it follow Clausius-Clapeyron, or will something else happen? Long-standing challenges in simulating land climate, including the diurnal cycle of convection, further highlight the shortcomings of our basic understanding. Okay, so obviously land has low heat capacity and gives you rapid warming, but also doesn't have any memory except in permafrost and snowpacks and land ice and so on. Looking at some of the theoretical understandings that, they say we need to go back to theory. to push the understanding further, instead of just relying on models which are always imperfect. And heterogeneity of land can be very, very, very high, right? That works at very small scales. If you look at any satellite map, there are meter scale ecosystems and meter scale land use changes and so on. So one of the topics here, land temperature and humidity changes constrained by tropical atmospheric dynamics. I have discussed this elsewhere. The role of convection and large-scale atmospheric dynamics in shaping tropical land temperature and humidity has been an important conceptual advance over recent decades. This framework emerged from efforts to understand why under climate change warming is stronger over land, the so-called land-ocean warming contrast. If global warming is happening and oceans warm slower than land, you will create pressure gradients associated with hydrostatic responses, and then you get certain wind responses associated with that. You add rotational effects and you may get winds that are favorable for upwelling, called cold ocean, warm land kind of issues that have been discussed for a while and so on. This framework emerged from efforts to understand this, and early explanations of this phenomena were based on the surface energy budget, radiative forcing at the surface, for example, due to increase in atmospheric CO2, are balanced in ocean regions largely by increases in evaporation, resulting in relatively small increase in surface temperature. On land regions, however, which are often water limited, radiative forcing is balanced primarily through increases in sensible heat and long wave fluxes, requiring a larger increase in temperature relative to oceans. Although physically intuitive, using this argument to construct a quantitative theory for land temperature change is challenging because surface fluxes depend on multiple factors aside from temperature, including wind speed, soil moisture, and the air's surface temperature disequilibrium, local effects, remote effects, wind dynamic effects, thermodynamic effects, vegetation effects, where evapotranspirations come in, and so on. Coming back to this in a minute, but let's look at the first figure. Land, you can see near surface warming is larger than ocean and global mean warming and has a larger range. Obviously very heterogeneous land use, as I said. Deserts are warming faster, and some other regions, India is cooling. We don't know precisely why, but we have these kind of heterogeneities in warming as well. But overall you have larger warming. Ocean, of course, is the lowest of the three because it also has high heat capacity, can hide away heat even though it's taking more than 90% of the additional energy we are trapping by increasing greenhouse gases. It warms the slowest of the three. Global mean, of course, is the average of those in some sense. There are details, is somewhere in the middle, but all of them have ranges, but land has a much larger range. If you look at the probability distribution function against normalized warming in degree C per degree C, so you have land here warmer with broader tail here, longer tail, and ocean has sharper peak, lower peak, and has smaller tail, maybe it's longer tail but thinner than the land. Okay, so I won't go more into that, but this is basically the multi-model mean probability density function of area weighted near surface warming over land and ocean, normalized by global mean warming in each model. The same models, simulations and averaging periods are used in panel A, and the wider land PDF in panel B suggests larger differences in near surface warming across space and also across models relative to the ocean. So oceans are being done more closely to each other in all these models. These models are not so independent. There's a lot of anyway, let's not go there. Okay, so coming back to the idea of what we were discussing in terms of land temperature and humidity changes constrained by tropical atmospheric dynamics, think about alternative framework inspired by reference 1, which I won't go to. You can look it up. This cuts through the complexity of land surface to reveal a strong constraint on the response of tropical land to climate change. This framework has transformed the understanding of the tropical land-ocean warming contrast and has led to broader insights into large-scale atmospheric controls on near-surface temperature and humidity. Let's just look at the reference since it's so directly being discussed. I shouldn't be lazy, but nonetheless, let's see. It is a paper by Joshi, Gregory, Webb et al. Says mechanisms for land-sea warming contrasts exhibited by simulations of climate change is a paper from 2008, but still is relevant. This paper just came out, that the one that I'm summarizing. Okay, so let's go back to reading this. So this framework has transformed our understanding. In the tropical atmosphere, strong vertical coupling by convection between the boundary layer and free troposphere described by convective quasi-equilibrium, together with horizontal coupling by gravity waves above the boundary layer, resulting in weak free tropospheric temperature gradients, imply that climatic changes in the adiabatically conserved quantities such as moist static energy, a function of temperature and specific humidity near the surface, are tightly coupled between different regions and therefore approximately uniform on large scales. So that's a lot of words in one long sentence. Typically we say a sentence shouldn't have more than 20 words, but here many ideas thrown together. There are reasons why the sensible heat and latent heat near the surface can cause air to rise, expand, cool, and or dry convection. So this is called the vertical convective coupling between land and atmosphere, but that also drives horizontal processes and coupling. And essentially then you have, if you get above the planetary boundary layer, just from observations we know that in the in the tropics, the atmospheric temperatures are pretty homogenized very rapidly, and that's called weak free tropospheric temperature gradients. This is also used in many ways called the weak temperature gradient assumption. It's not an assumption, but then using that to explain dynamic constraints. I have done one podcast on understanding how wet bulb temperature may be constrained by this weak temperature gradient as well. Okay, so that's the main point they're trying to make here as well, in terms of how land looks very heterogeneous and local, and yet you have this large scale constraint that must be considered. Let's just look at figure 2 here before we go back. Atmospheric dynamics constrain changes in tropical land climate. So you can see convection and gravity waves in the tropical atmosphere spatially homogenize climatic changes in near surface moist static energy, MSE, which is important for instabilities and other processes that drive atmospheric circulation. I have basic podcasts on that that you can follow up. The development of this large-scale atmospheric constraint on the tropical land climate has been an important conceptual and advance over recent years. Here and in figures 3 and 4, the tidal maps highlight where the mechanism is broadly expected to be applicable. So here you are looking at the tropics identified and vertical and horizontal mixing, homogenizing changes in near surface energy across tropics. Okay, even though there are planetary boundary layer processes and vertical processes, horizontal gravity wave smoothing of the temperature gradient above the boundary layer provides a dynamic constraint. So here you are looking at that with land shown as heterogeneous region, and you have convection being shown, which is of course lifting moisture from low level convergence, free tropospheric convergence, pumping through the planetary boundary layer, expanding into the convective regions of the free troposphere, and then you have local cycle that works like this: convergence, ascent, and divergence and descent. And you have mixing air vertically from boundary layer to free troposphere, mixing temperature and humidity effects to coming from the other side, tropopause being homogenized in terms of temperature by gravity waves, so homogenized free tropospheric temperatures across the tropic, homogenized near surface moist static energy changes as well, and that gives you a constraint on exactly how the land climate works in the actual system. Okay, this mechanism, a form of downward control exerted by overlying atmosphere on near surface tropical climate, has important implications, although temperature and specific humidity individually may respond differently to climate change in different regions. For example, in tropical savannas versus rainforests, the combined change encoded in moist static energy is more spatially homogeneous. Local processes including soil moisture and aridity are crucial for controlling how temperature versus humidity changes contribute to the change in moist static energy imposed by the atmosphere. So you can see the scales are very different, and yet they are getting constrained by this dynamic at large scale. This physical theory underpins advances in understanding the land-ocean warming contrast, aridity, and land relative humidity in a changing climate and extreme heat. Ocean offers a very smooth, homogeneous surface and very high heat capacity, and this establishes a simple yet quantitative framework for interpreting models, observations, and the roles of local versus large-scale, I'm having hiccups, processes in shaping tropical land climate. Okay, so another figure here, they talk a little bit about theoretical understandings needed in evapotranspiration. Here we are looking at a schematic. Evapotranspiration inferred from temperature and humidity measurements. Following recent theoretical developments, inland ET can be predicted as simple function of near surface temperature and humidity along the net radiative flux into the surface. Note that gray arrows represent the series of inferences used by the SFE based theory to make estimates of ET, whereas the blue and orange arrows denote respectively the turbulent fluxes of heat and water coupling the surface to the near surface and the radiative energy fluxes. Okay, so near surface temperature and humidity predict evapotranspiration. You know already what evapotranspiration is, or you can follow up. So you're looking at very close to the surface, 2 meters, and surface obviously has vegetation and other land use types, and evapotranspiration is evaporation mediated by biology, and you have humidity and temperature again being critical parameters that give you the coupling by turbulent fluxes, and you look at bound ratio, which is a ratio of fluxes latent and sensible, and that adds to your radiative flux processes that are going on in terms of incident and reflected or scattered, that together determine evapotranspiration. Let's just make sure we state SFE properly, and as you know by now, I read and then I forget the acronyms. This is the surface flux equilibrium. The theory based on the concept of surface flux equilibrium, or SFE, assumes an approximate balance between surface moistening and heating effects on near surface relative humidity. Okay, so that gives you basically a strong coupling at rapid time scales. Okay, what are the opportunities for progress? A greater emphasis on developing theories for land climate and its change is essential for building confidence in future projections, identifying directions for model improvement, validating in situ and remote sensing data, and interpreting the dynamics of key processes as new models and observational systems come online. The examples highlighted in the preceding demonstrate that in the preceding sections, I guess, demonstrate the potential for theory to further as in the verb, for theory to further fundamental understanding of land climate. But the next set of advances is now needed. In the following we present three areas of land climate science primed for theory to provide new insights. Okay, Atmospheric circulation and land. I'm going to read this whole section because it's relatively short and that's the main message from this group. The atmospheric circulation strongly shapes the land climate from extreme temperatures to the regional water cycle. However, much of our understanding of the atmospheric circulation and its sensitivity to climate change has been developed using aquaplanet models without land surfaces. Over recent years, focus has begun to shift towards incorporating land into conceptual frameworks for atmospheric state and circulation, but numerous basic questions persist. Why is the tropical rain belt wider over the continents? If you look at the IPCZ, it's narrow over the oceans relative to the land. How can ingredients of land surface incorporated into modern theories? So how can ingredients of the land surface be incorporated into modern theories for monsoons? And now you're talking about global monsoons. Why is the poleward expansion of the atmospheric circulation under global warming much weaker over land? How will blocks, often the cause of extreme weather over land, change with warming? The atmospheric pressure blocks. What processes control updraft velocities and hence the influence of extreme precipitation over land? Hence influence. Okay, let me read it again. What processes control updraft velocities and hence influence extreme precipitation over land? These important questions are ready to be tackled with new theories. Maybe AI will begin to play into this as well. Already is, but there's often not enough data for global scale understandings. Water and land. Beyond a broad tendency for mean relative humidity over land to decrease with warming, basic properties of the land water cycle and its response to climate change remain unexplained. For example, what are the mechanisms determining the spatial and temporal distributions of soil moisture in the current climate? Remember, soil moisture is a very small scale quantity. Decorrelation scales are small, and it plays a very important role in memory, local convection, recycling, maybe even cyclones, as some papers have reported in terms of what happens to the cyclone when it crosses over to land and so on. And yet we have to remember the large scale dynamic constraint from the weak temperature gradient. Okay. Why do climate models project drier surface soils in most regions? Why do future trajectories for surface and column soil moisture differ? Detailed understanding of near surface humidity over land is another priority, given the strong coupling to trends in extreme temperatures, extreme precipitation and runoff. So soil moisture can also make a difference in terms of how quickly extreme temperatures evolve. The coupling between plants and water has major implications for drought and terrestrial ecosystems, yet its response to climate change is highly uncertain. For example, the effects of plant changes on runoff beyond the simple CO2 stomatal dependence are probably very large but poorly understood. Finally, the phenomenon of flash droughts, whose dynamics and predictability are only beginning to be explored, is an emerging topic where creative new theories are needed. So this CO2 stomatal dependence is basically stomata is open to capture CO2, but they want to minimize water loss that they have lifted with great trouble from the root system. And when CO2 increases, there is the CO2 fertilization effect that stomatas don't have to open for very long to capture the same amount of CO2, so they lose less water in the process, and then there are many debates about what happens beyond that. Carbon and land. Carbon uptake and release by terrestrial ecosystems both affects and responds to climate variability and long-term change. The field of carbon-water climate feedbacks is already rich with examples of simple concepts, theories, and emergent constraints, providing a way to synthesize or contrast the behaviors emerging from complex Earth system models. The carbon concentration and carbon climate feedback parameters, for example, encapsulate the overall response of land carbon stocks to changes in atmospheric CO2 and to global warming, respectively. This global scale conceptual framework can be used to diagnose and compare complex simulations, but it's also transferable to climate emulators or models of reduced complexity. Full ESMs are very computationally expensive to run, but you can create these emulators which capture the most important processes with some criteria and can be run many times to look at various realizations of climate responses. Okay. However, similarly simple and adaptable concepts are lacking in other areas of carbon cycle research. There is, for example, large uncertainty on the extent to which tipping points at regional scales could impact some of the world's largest carbon pools, such as permafrost carbon, the Amazon rainforest ecosystem, and global forests as a whole. To some extent, this is because we lack theories, metrics, and frameworks to explain and reconcile the contradicting results obtained from different models and approaches. However, the existing literature on dynamical systems theory is rich with concepts that may be transferable to understand potential tipping points in the carbon cycle if they can be adequately constrained by observations, similar to what has been done to study transitions between stable system states or attractors in ecology and population dynamics. In general, tipping points are tricky because the models are not doing them. We don't have very good data for them, and they are hard to predict because you don't know them till they happen. But nonetheless, you have ideas like permafrost, which has locked up a lot of methane, carbon dioxide. If it begins to melt, will it flip at some point and just completely disappear? But there are complications because when permafrost thaws, lake ponds form, and then other forms of carbon uptake happen, and so on and so forth. So here is the stomatal response to increasing CO2 that boosts river runoff, because if they lose less water vapor to the atmosphere, that's often going to be rejected. That's the idea. The competing effects of temperature versus CO2 on evapotranspiration from leaves and on river runoff. The recent incorporation of the CO2 effect into classical theories has clarified understanding of runoff in a changing climate. So we're looking at a global map. As CO2 increases, plants limit evapotranspiration and boost river runoff. Okay, so basically loss of water is reduced. Leaf stomata effect, wide stomata, so you are seeing H2O loss here in the present day, but with wide stomata, with increase in temperature, you may lose more water vapor because vapor pressure deficit is higher when atmospheric temperature is warmer, because warm temperatures hold more water, warm atmosphere is thirstier. But if you have narrow stomata, if stomata can narrow, increase in CO2 can reduce the water vapor loss. So runoff here, let's say the standard natural variability, less water available for runoff, so you reduce the runoff, but more water available for runoff if the stomatas become narrower and reduce the water loss through stomata and instead put it back into the ground. What are the outlooks to discover, test, and refine the powerful theories for land and land climate advocated in this perspective, and to maximize benefits for the wider climate community? Technical tools and scientific talent are needed. On the tools side, we have at our disposal a range of models spanning idealized to state-of-the-art Earth system models alongside the emerging generation of global storm resolving models and flexible process-based hydrologic models. This model hierarchy is well positioned for building new understanding of land climate. However, a lack of observations presents a major challenge despite recent progress. For example, in remote sensing of surface soil moisture, we simply do not have long-term datasets with widespread spatial coverage for many important land climate quantities, including root zone soil moisture and ETs. Satellites do a great job for soil moisture, well, good enough job, but root zone soil moisture remains a problem. Thus, to parallel the development of models and efforts to construct theories for land climate, new instrumental observations of essential land surface fluxes and reservoirs are required. Opportunities to further leverage existing observational data sets with the goal of improving models and testing theories should also be exploited. Beyond observational uncertainty, whenever we ground new theory In observations, we also have to contend with the complicating influence of internal climate variability. In other words, not everything is necessarily related to anthropogenic change. Just random variability in the system can produce a lot of apparent variability that has to be understood in terms of external forcing and internal variability. Separating the forced response from internal variability at regional scales is still challenging and can harbor surprises that can influence our theories. Empirical statistical methods to isolate the forced response and new theory on internal variability itself will thus need to accompany our endeavors to refine understanding of land climate and its changes with warming. Again, AI is being used a lot. On the talent side, to tackle important questions in land climate science, we need to continually inspire, recruit, and resource diverse cohorts of researchers from a range of primary disciplines spanning atmospheric science, hydrology, ecology, physics, mathematics, computer science, and beyond. This is a very standard statement, but we need to keep repeating it anyways. Engaging scientists from the broader climate community, those working primarily on atmospheric dynamics, for example, also have the potential to bring new ideas and drive progress in land climate science. Through this perspective, alongside a series of workshops and summer schools, we aim to coordinate over coming years. Our goal is to engage. Sorry, did I miss it? Yeah. Let's read again. Through this perspective, alongside a series of workshops and summer schools, we aim to coordinate over coming years. Our goal is to engage these current and future generations of researchers, as well as major funding bodies and established land-focused research initiatives in our vision to place theory at the core of land climate science. The sentence is a bit awkward, but you get the sense. And funding resources, bringing them together. Now you know what's happening in the US, so everything is up in the air. State-of-the-art models, observational systems, and machine learning are transforming our ability to simulate, monitor, and emulate many aspects of land climate. Our scientific understanding, however, has not kept pace, and we now lack robust theories to comprehend the research complexity being revealed by these advanced tools. Now is the time to change course and underpin models, observations, and machine learning techniques with new theories so that we maintain and advance the deep mechanistic understanding of land climate needed to meet the challenges of an uncertain future. We live on land and we need to understand more, that's obvious, but what are the gaps, where do we need to go, and so on are tried to be captured here. It's focused much more on theory, but you get a sense of where the models need to improve as well in terms of representing the processes, and ultimately it comes back to improving land climate variability and change so that overall climate predictions and projections have to improve, including the impacts, right? That's where people live. Agriculture, water, health, energy, everything is going to be depending on land climate. Okay, let's leave it here.